Good morning everyone. I Aditya from BSC Chemistry on the second year is today here to explain the chapter IR Spectroscopy for the presentation in 4th semester. Let's start with the content we study in the following presentation. Firstly, we will do some introduction about IR spectroscopy, then we will discuss about principle of IR spectroscopy, then we will discuss the type of vibrations, factors influencing the vibrational frequency, instrumentation, application of IR spectroscopy in our daily lives. Let's start with the introduction. Infrared spectroscopy, or it is also known as the vibrational spectroscopy, it is concerned with the study of absorption of infrared radiations which result in the vibrational transitions. Radiations refers broadly to the part of electromagnetic radiations that lies between the microwave or visible region. As you see in the figure, it will ranges from 1 micrometer to 200 micrometer. It also consists of the three parts. First one is near IR, which ranges between 1 micrometer to 5 micrometer. The mid IR that ranges between the 5 micrometer to the 30 micrometer, and third one is 330 micrometer to the 200 micrometer. Let's see the principle of IR spectroscopy. When the frequency of IR radiation is equal to the natural frequency of vibration, the molecule absorbs IR radiation and a peak is absorbed. Every bond or the portion of a molecule or the functional group requires different frequency for the absorption. Here it is the principle of IR spectroscopy. Let's start now with the theory. The infrared radiation does not have the enough energy to induce the electronic transitions as seen with the UV, that is ultraviolet radiations. For a molecule to absorb the infrared radiations, it must be accompanied by a change in the dipole moment. Regions of the wavelength range. There are three regions as we have already seen in the upper part. First one is very near IR, which is also known as Overton region, ranging between 2 to 2.5 micro. And second one is near infrared, that is also known as vibration region, that is lie between 2.5 to 225 micrometer. And third one is far IR. It is also known as rotational region, that ranges from 25 to 400 micrometer. Hooke's law. It is also used in the IR spectroscopy, in which a mass m1 and a mass m2 are placed at some distance k, and the frequency is led by the 1 upon 2x under root k upon mu, whereas mu is the reduced mass calculated by the summation of two mass when in the denominator and upper part by the multiplication of both the masses. Then by putting the values we will get the frequency. The type of vibration in the IR spectroscopy. There are different types of vibration. First one is stretching, that is symmetric or symmetric. Second type is the bending. It is also of two types: in plane bending, that is scissoring or rocking, or the out of plane bending, which is also further divided into two types, that is wagging or twisting. Now see all the bendings one by one. Symmetric stretching vibration. Here both the outside atoms move away from or towards the center. Here you can see the blue and the red one moving away from each other. Second one is the symmetric bending or the vibration in a plane. It is also known as scissoring, as you see both the molecules are coming towards each other. Symmetric bending. It is the bending in which the vibration are of the out of the plane moving anticlockwise and clockwise respectively, or also known as twisting. Third one is asymmetric stretching. Asymmetric stretching vibration is as one atoms move towards the center and second ones move away. Here we see that the red one is moving towards the center and the blue one is away from the center. Asymmetric bending. Vibration in a plane is also known as rocking, in which both the molecules are ranging from clockwise in direction. Asymmetric bending, vibration out of a plane. Here it is also known as wagging. Now see what are the factors influencing vibrational frequency. First of all, the symmetry. The symmetry affects as the symmetric compounds do not possess the dipole moments and are IR inactive, which means they do not absorb any IR radiations. Here we have taken example that is symmetric acetylene having formula C2H4 having the triple bond introduced between the two carbon atoms and then are adjacently joined by the hydrogen atoms. Second one is Fermi resonance. Fermi resonance also affects the vibrational frequency as it results in an unexpected shift in the energy and the intensity of the bands. Example: the overtone of CH deformation mode at the 400 per centimeter is always in Fermi resonance with the stretch of the same band at the 2800 per centimeter. Third factor influencing is hydrogen bonding. Hydrogen bonding brings about the remarkable downward frequency shifts. In the intermolecular, the broad bands are observed, whereas in the intramolecular, the sharp bands are observed. The here intermolecular is refers to the between the two molecules of same atoms, whereas intramolecular is within the atom in the same area. Fourth factor influencing is electronic effect. Electronic effects such as inductive, mesomeric, and field effect may cause shift in the absorption bands due to change in absorption frequency. Example: inductive effect, whereas the acetone having the vibrational frequency 1715 per centimeter and chloroacetone having the frequency 1725 per centimeter, whereas the mesomeric effect also influence the vibrational frequencies as the acetophenone have the vibrational frequency 10693 per centimeter, whereas the para-amino acetophenone having the frequency 1677 per centimeter. Fifth factor influencing is the bond angle. The difference in the bond angle also led to the change in the absorption bands. Example: here in the first figure it is of the three molecules having the vibrational frequency 1815, whereas in the four angles it is 1780. As the angle increases, the vibrational frequency decreases. It is also known as ring strain. More the angle, less will be the strain. The instrumentation involving in the IR spectroscopy are the main parts of the IR spectrometer, which helps in the ranging of IR radiation among the molecules. The first factor is IR radiation sources. Second is monochromators. Third one is sample cells and sampling of the substance. Fourth factor is detectors. Here the sequence will follow. First of all, a source is placed, then a sample, then the light will pass through the monochromator, then detector, and then the light will be read out. This following the sequence in the principle of IR spectroscopy. Now see all the instruments one by one. First of all, the IR radiation sources. The radiation source must emit IR radiation, which must be of intense enough for detection, steady, extend over the desired wavelengths also. The various popular sources of IR radiations are: first one is incandescent lamp, second one is Nernst Glover, third one is Glober source, and fourth one is mercury arc. These four are the popular sources which led to as a source in the ejecting the IR radiations among any sample. Radiation sources. They must produce intensely and steady radiation. As we see, the Nernst Glover having the composition heated earth rare oxide rod made up of zirconium, yttria, and thoria K, having the temperature nearly about 1500 Kelvin and having the range 1 to 50 micrometer mid to far IR, as we see the parts of near IR. Second one is the glober. It is made up of by heating the silicon carbide rod at the temperature of 1500 Kelvin, and it also have the range between 1 to 50 micrometer, ranges from mid to far IR radiation. Third source is W, means tungsten filament lamp. It is operated at the temperature of 1100 Kelvin, having the IR range between 0.78 to 2.5 micrometer, nearly about near IR. Fourth source is the mercury arc lamp. It is made up of mercury plasma having the range between 50 to 300 micrometer from fire IR. Third instrument is monochromators. It is made up of prism and can be used as dispersive element. The constructed of various metal halide salts. Also, the sodium chloride is the most commonly prism salt used. Here we can see, first of all, a prism is placed among sample and detector is in the form of laser, and the photodiode is also present, having the mechanism as shown. Here we will see the wave number and absorption graph is plotted where we will see the different type of peaks. Second part is grating. Grating are nothing but the rulings made on the some materials like glass, quartz or alkyl halides depending upon the instrument. The mechanism is that diffraction produces reinforcement. The rays which are incident among the gratings get reinforced with the reflected rays. As we said, the difference grating first IR incident beam is incidented on the diffraction grating, and we will see the three waves ejecting out V1, V2 and V3. Third one is the sample cell and the sampling of substance. Infrared spectra may be obtained for the gases, liquids or even about the solids. Material containing sample must be transparent to the IR radiation, so the salts like sodium chloride, potassium bromide be used. Let's see, we are using the potassium pellet press to compress the sample and the liquid cell. For that, sample handling. Samples of the same substance shows shift in the absorption band as we pass from solid to gases, and hence the samples of different phases have to be treated differently in the IR spectroscopy. Sampling of liquid solids. Sample handling. Samples of the same substance show shift in the absorption bands as we pass from the solid to the gases, and hence the samples of different phases have to be treated differently in IR spectroscopy. The sample of solids consists of four phases, that is solid runs in the solution, melt technique, pressed pellet technique or the solid films. First one, the solid runs in the solution. Firstly, dissolve the solid sample in a non-aqueous solvent and place a drop of this solution in the alkali metal disc and allow to evaporate, leaving a thin film which is then mounted on a spectrometer. Example of the solvent: the acetone, cyclohexane, chloroform, etc. Mull technically, finely powder sample plus mulling agent nuzole, make a thick paste. Mull, transfer the mull to the mull plates and the plates are squeezed together to adjust the thickness, is then mounted on the spectrometer. Third one is pressed pellet technique. Finally, the powdered sample is mixed with the about 100 times its weight of K in the potassium bromide in a vibrating hole mill, and the mixture is then pressed under very high pressure in a die to form a small pellet 1 to 2 mm thick and 1 cm in diameter. Here you can see from a vacuum we will add the piston, tons of pressure, then dye, sample mixture and dye are squeezed. Solid films. Here the amorphous solid is dissolved in the volatile solvent, and this solution is poured on a rock solid plate that is consist of the sodium chloride or the potassium bromide, and then the solvent is evaporated by the gentle heating. Sampling of solid. Liquid sample can be sandwiched between the two alkali halide plates between sodium chloride, potassium bromide and calcium fluoride. The sample thickness is ranges from 0.01 to 0.05 mm. Here you can see there is a NaCl plate, liquid sample and NaCl placed. The liquid sample is placed between two, it means it is sandwiched. Sampling of the gases. Here, gases sample is introduced into a glass cell made up of the sodium chloride. Very few organic compound can be examined as gases. For example, the 1,4 dihexane is sampling as the gases. Detectors. The detectors can be classified into the three categories. The first one are the thermal conduct detectors. Their responses depends upon the heating effect of the radiation. Second one is the pyroelectric detectors. The pyroelectric effect depends on the rate of the change of the detector temperature rather than on the temperature itself. The third type of the detector is photoconducting detector. They are the most sensitive. Detectors. First one is the thermocouple. It is composed of the thermoelectric effect is similar metal junction, and its advantage is it is so cheap, also slow and insensitive. The second one is bolometer. It consists of the nickel platinum resistant thermometer, or if we can call it thermistor. It is highly sensitive with the less than 40 per centimeter. The third one is the Goli cell. It is made up of the metal cylinder with the xenon gas. Its advantage is that it is faster than others and having a wide wavelength range. The fourth one is pyroelectric. It is composed of the triglycerin sulfate piezoelectric material. It is also fast and sensitive, and its range lie between the mid IR. The fifth one are the photoconductive non-thermal. They are consisting of the lead sulfate, cadmium sulfate, lead cesium, light sensitive cells. They are also fast and sensitive, and they are lie in the near IR region. Dispersive IR instrument. The dispersive IR instruments are introduced in the 1940s. These are mostly used in the single beam experiments. These are double beam instruments. In dispersive IR, sequential scanning of wave numbers of light take place. It is shown like that in real lives. Fourier transform IR instrument. Its full form is FTIR. It collects all the wavelengths simultaneously and at once. It is work on the Michelson interferometer, which having the beam splitter, fixed mirror and the movable mirror. FTIR instrumentation is shown below. Here we have taken an interferometer, a detector, the glasses for the refraction, the sample chamber, and we will also introduce a helium neon gas laser. Firstly, the light source. From the light source, the beam are touching the mirror and projective towards the fixed mirror, then the movable beam splitter, and we will finally see the different wavelength at a one time. Now see the applications of the IR spectroscopy. First of all, we can identify a organic compound. It is to measure the spectrum. No two samples will have the same identical IR spectrum. Let's see. Here we can see that all the atoms or compounds having the different IR spectra. Now we will see the fingerprint region. The absorption band in the region between 1500 to 500 per centimeter. It is useful for establishing the identity of a compound. It consists of a region that is 1500 to 350. It means the appearance of doublet near 380 per centimeter and 1365 per centimeter. It shows the presence of 3-degree butyl group. Also the region between 1350 and the 1000 per centimeter, all classes of compound which alcohol, esters, lactone shows absorption in the region due to CO stretching. The region below 100 per centimeter. This region distinguishes between the cis and trans alkene. Now the second factor is the qualitative determination of functional groups. It is its set in applications. The presence or absence of the absorption bands help in predicting the presence of certain functional groups in the compound. Here we can see that the triple bond having the wave number between 2260 and 2220, whereas of the double bond it is 1680 and 1600, and the intensity is in both the peaks are the medium. Hence, we see that all the different bonds having the different wave numbers. The third application, it is used in qualitative analysis. It can be done by measuring the intensity of the absorption bands. This is done by the baseline technique and is used to determine the quantity of a substance. By using the Beer-Lambert law, the expression is A is equal to log I naught upon IT is equal to epsilon BL or equal to minus log T, whereas A is the absorption or the optical density simply defined by OD, and epsilon is the absorptivity per mole per centimeter, and C is the concentration measured in molar, and T is the transmittance. Fourth application in the identify the impurities in a drug sample. The impurities having the different chemical nature when compared to the pure drug. Hence, these impurities give rise to the additional peaks than that of pure drug. Hence, we can identify the impurities in a drug sample by the IR. By comparing these, we can identify the presence of the impurities. The limitation of the infrared spectroscopy. As we know, every instrument or every technique has some limitations also. By IR spectroscopy, it is not possible how to know the molecular weight of a substance. We can also only find the number which substance is present. We can't measure its quantity. It does not provide information of the relative positions of the different functional group on a molecule. Also, from a single IR spectrum of a unknown source, it is not possible to know whether it is a pure compound or a mixture of compound. We can only show the presence, not the purity. Thank you for listening.